Okay, here's the recording in progress. So let me share the screen. Okay, so we're up to here. Should be done with 10.2 today. Maybe sneaking a little bit of 10.3. Okay. And a reminder, I've sent out the URL for the polar graph paper. Make this a little bit smaller. Okay, it should look like this. So look under yesterday's Canvas announcement should have this. Okay, so it looks like this. It's every 15 degrees. 1, 2, 3, 4, 5, 6. 6 marks between 0 and 90 degrees. So these are 15 degrees apart. There's 14 concentric circles. If you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, and to make it fair on everybody, and I want you to be able to figure things out for yourself. So everybody, please use exactly this paper. If you don't use this paper, I may take off points. Okay, so that's what I want you to use. And we'll be using that maybe starting tomorrow, if not the next day. So we'll see how that goes. Okay, so look for the URL. You can find it under mathbits.com. Okay, get this thing focused here. Mathbits.com. All right, so I will do some more problems from 10.2, sneak in a little bit of 10.3 on polar coordinates, maybe not start any problems, but at least give you the formulas that you need, and then we'll go from there. Okay. Let me jump back and do number 7. Let me show you the wording for number 7. Okay, 7, find the equation of the tangent of the curve by 2 methods without eliminating the parameter. In other words, don't get rid of the t. And B, first eliminating the parameter. So get rid of the t. If you get rid of the t, it becomes a Calc 1 problem for finding the equation of the tangent to the curve. Okay. So part B, by transforming it, it becomes a Calc 1 problem. All right, so the first part though, part A, don't eliminate the parameter, do it by this new technique. So here we go. X equals 1 plus ln t, y equals t squared plus 2. The point is 1, 3. I need to find a corresponding t value. This one, I'd have to do a plus or minus, but this one, I don't. But let's go ahead and figure that out here. So if I plug in 3 right here, right, I'm at the point 1, 3. That means this is 1, this is 3. So 3 equals t squared plus 2. T squared is 1. T is plus or minus 1, but negative 1 is not allowed for x. You cannot take the ln of negative 1. So that tells me we only have t equals 1. Okay, so the time, I suppose, t is 1. Quick double check. 1 plus 2 is 3. 1 plus natural log of 1 is 0. So you do get 1. So it works. All right, so dy dx by formula. Put it on your cheat sheet. dy dt divided by dx dt. Okay, so that should be pretty straightforward. dy dt is 2t. dx dt is 1 over t. And clean this up. If you divide by a fraction, you multiply by the reciprocal. So 2t times t over 1. And so it comes out to be 2t squared. And I just plug in t equals 1. So I had to figure out the t equals 1, right? So dy dx is 2 times 1 squared, 2. Okay, so just do the point slope form, point, slope, derivative. So y minus y1 equals m times x minus x1. And you can stop there. You don't have to go farther if you don't want to. Okay, part B says eliminate the parameter. That means get rid of the t. Okay, it's probably easier to get rid of the t in the first equation, because again, here, if you try to isolate the t, somewhere you'd have to take a square root that involves a plus or minus, and I don't want plus or minuses. So I'd rather work with the first equation. So I subtract 1 on both sides. So I have x minus 1 equals ln t. Get rid of the ln by exponentiation. Put an e here and an e here. These guys cancel out. So t is equal to e to the x minus 1. And now I take that expression and plug it in for here. Y is t squared plus 2. So y is t e to the x minus 1 squared plus 2, t squared plus 2. And then you multiply this out, e to the 2x minus 2 plus 2. So now it just becomes like a Calc 1 problem, right? Calc 1, y as a function of x. This is a Cartesian equation, meaning there's no more x. There's no more t. And find the derivative and the equation of the tangent at 1, 3. So just like in Calc 1, I take y prime. The derivative is going to be the same thing as this, except times 2 by the chain rule, and the derivative of 2 is 0. So y prime is 2 e to the 2x minus 2. And I'm plugging x equals 1. So put a 1 there, I get 2 minus 2 is 0, e to the 0 is 1, so 2. So of course you get the same answer. Y minus 3 equals 2 times x minus 1, and that's exactly what we got way over here. Okay. All right, then go back and do number 9. Find the equation of the tangent to the curve at the given point. Then graph the curve and the tangent. You don't have to graph. Okay, so x is equal to t squared minus t. Y is t squared plus t plus 1 at the point 0, 3. Okay, so they give me the point. I want to translate that to a t value once again. So 0, 3. This has to be 0. This has to be 3. So let me solve this for 0. That's easy. 0 equals t squared minus t. Factor out a t. So t equals 0 or 1. But if I plug in here, if I plug in 0, I don't get 3. If I plug in 1, I do get 3. So that tells me t equals 1. Okay, so when I plug in for t, I'll be plugging in t equals 1. All right. So by formula, dy dx, again, put it on your formula sheet. Dy dt, 2t plus 1. Divided by dx dt, 2t minus 1. And then I plug in 1. So 2 times 1 plus 1, 3. 2 times 1 minus 1, 1. 3 divided by 1 is 3. That's it. Y minus y1, y minus 3 equals m 3 times x minus 0. You could leave it like that, or if you want to clean it up, I mean, x minus 0 is just x, so y equals 3x plus 3. Okay, so remember the point slope form, y minus y1 equals m times x minus x1. Right? Point slope. Point slope form of the line. Okay. All right, so that's it for that. And now the only other parts I was going to show you were at the very end, where we do arc length. So these problems at the very end. Which would be 41, 43, 45. So I'll show you a couple of those. So that's where I'm going to use this thing. Page 653, arc length. Now you might say, well, didn't we already do arc length? Yes, that was either y is a function of x or x is a function of y, but not parametric equations. So for parametric equations, I use this. And again, put it on your cheat sheet. If x is a function of t, y is a function of t, you do this thing. So you go from alpha to beta. This is alpha, this is beta. Integrate with respect to t, the square root of dx dt squared plus dy dt squared. Okay. I'll show you a couple of those. Okay. See, 41. X equals 1 plus 3t squared, y equals 4 plus 2t cubed. T goes from 0 to 1. Okay, this has some curve. We don't really care what it looks like. I mean, you know, you could plot points. I can make a table. In fact, plugging in 0 and 1 should be easy. Plug in 0, you're at what, 1, 4? Plug in 1, you're at 4, 6. And then in between it does some curvy thing. So whatever it looks like, we're trying to find the arc length. If I walk along the curve, how far would I have walked? Okay. So hopefully it's pretty straightforward. Find dx dt, derivative of this is 6t. dy dt is 6t squared. By formula, I'm supposed to square them. So if you square that, it's 36t squared. Square that is 36t to the 4th. And when you integrate, take the square root of the sum of squares. So the arc length is the integral from 0 to 1. They told me to go from 0 to 1 of the square root of 36t squared plus 36t to the 4th. Factor out the 36t squared, 1 plus t squared. This thing comes outside, becomes 6t. I don't have to worry about absolute value because I'm between 0 and 1. So 6t. Now here's a trick you may not have seen before. For some strange reason, I'm going to change the 6 into a 3 times 2. Can you see why I want to do it that way? To plan for my u substitution, right? What's the derivative of 1 plus t squared? 2t. Right, so that's the reason why I broke it up that way. Now you say, do I have to do it? No, you could just take out the 6, and then you would have done what? You would have put a 2 here and a half outside. You get the same thing. But this is a little bit faster if we do this technique. All right, u substitution. U equals 1 plus t squared. Du is 2t dt. So there's my 2t dt, which changes to du. There's 1 plus t squared, which changes to u. And I change the limits. When t is 0, plug in 0, u is 1. T is 1, plug in 1, u becomes 2. So my new integral is from 1 to 2. Radical u du. Okay, so we played that game before. 3 times, that's u to the 1/2, right? So u to the 3/2 divided by 3/2 means times 2/3. Looks like the 3's cancel out. Become 2. So I have 2 to the 3/2 minus 1 to the 3/2. And you know the way that we want to write something to the 3/2. 2 times 2 radical 2 minus 1 to any power is just 1. So this is the best final answer. 2 times 2 radical 2 minus 1. You can leave it like that, or if you want to distribute, that's okay too. But pretty much that's what we got here. Yeah. All right, and the only other one I was going to show you was 45. And I think I'll be done with this section. 45. Yeah, there's a graphing calculator icon. Don't worry about that. And never mind about the graph. Don't graph the curve. We are going to find its exact length. So x equals blah, 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 y equals blah, blah, blah. Whatever it looks like has some funny shape between 0 and pi. We're finding the arc length. If I walk along that curve, right, how far would I have walked? Okay. Here we go. Okay, x equals e to the t cosine t, y equals e to the t sine t, t going between 0 and pi. All right, so it looks like I got to do some product rule here, right? Several times. So dx dt, product rule, first times the derivative of the second, e to the t times negative sine t, plus second function times derivative of the first. So cosine t times the derivative of e to the t is itself. Okay, and if you factor out an e to the t, you have cosine t minus sine t. dy dt, also a product rule. First times derivative of the second, e to the t cosine t, plus second function, sine of t, times derivative of the first, which is still e to the t. Factor out e to the t, cosine t plus sine t. All right, now I'm supposed to square each of these guys. So what is dx dt squared? So if I square this, the square of e to the t is e to the 2t. And this cosine t minus sine t, right? So that's my a squared minus 2ab plus b squared from algebra. Right, so it's cosine squared minus 2ab minus 2 cosine t sine t plus sine squared of t. Okay, and I notice that these two give me 1 cosine squared t plus sine squared t. So I'm going to write it as e to 2t parentheses 1 minus 2 cosine t sine t. And then something similar happens for dy dt squared. That's supposed to be dy dt, not dy dx. So to square this, I have e to the 2t. And now I'm squaring a plus b. A squared plus 2ab plus b squared. It's essentially the same as this, except this minus becomes a plus. So cosine squared t plus 2ab, 2 cosine t sine t plus sine squared t. Once again, these two combine to give me 1 cosine squared t plus sine squared t. So I have e to the 2t, 1 plus 2 cosine t sine t. Now, the reason why I circled this and circled this is by formula, I'm supposed to add these two together, dx dt squared plus dy dt squared, right? So by formula, I'm supposed to add them up. Show you that formula very quickly in the book. This thing here, page 653. Put it on your formula sheet, right? So I need dx dt squared plus dy dt squared. So in other words, I want this plus this. So dx dt squared plus dy dt squared. So if I add these two together, I can factor out the e to 2t. I have 1 minus 2 cosine t sine t plus 1 plus 2 cosine t sine t. Well, these two are going to cancel out, right? And then I just have 1 plus 1, which is 2. So 2 e to the 2t. Okay, so one more time. Everything here circled plus everything here circled. You add them up, this is what you get. All the trig cancels out. Again, you can factor out the e to 2t. It's 1 minus that plus 1, 1 plus 1 is 2, then plus this. So these two cancel out. And this goes underneath the radical. So finally, I'm ready to integrate, and it's a pretty easy integration after that. So arc length is the integral from 0 to pi of square root of dx dt squared plus dy dt squared. Now the square root of this. The square root of 2 is just the square root of 2. I took that outside. The square root of e to the 2t is e to the t. Because you say to yourself, what do you square to get that? You square e to the t. E to the t times e to the t is e to the 2t. All right, so we're pretty much home and free now. Integral of e to the t is itself radical 2 e to the t from 0 to pi. So radical 2 e to the pi minus e to the 0, which is 1. So this is the best final answer. Radical 2 e to the pi minus 1. All right, folks, and I am now officially done with 10.2. I'll sneak in some of 10.3 to get a little bit ahead. Okay, the topic is now polar coordinates. Now, you won't need to graph anything today, but there's a very good chance I might start some of this tomorrow. So look on mathbits.com, or actually look at the URL I gave you. It's a little bit smaller. Okay. So look under Canvas announcements. Yesterday's Canvas announcements, I sent the URL link for this particular polar graph. You're going to need about 20 total. Okay, give or take a few. If you're perfect and you never make a mistake, okay, you can probably get by with maybe 15. Okay, but just in case you mess up like me, have this ready. Okay, so be ready for it possibly by tomorrow. All right, so I'll introduce polar coordinates. Won't get that far. And then that'll be it for today. So polar coordinates. So it's a new coordinate system. So instead of x comma y, we have something called r comma theta. It's a different coordinate system. Cartesian coordinates, that's our usual x and y. We have a new system, polar coordinates. Okay. So the text gives you these, but I'm going to show you this figure, which is more useful, on page 659, figure 5. Okay. If you want to put this on your formula sheet, you may. All right, here's a point we're familiar with, x comma y. Means start at the origin, how much do I go in the x direction, how much do I go in the y direction. Out of convenience, we put it in the first quadrant, but it can be in any quadrant. Right, so you give me a point, right? 3 comma 5. You say, okay, I go 3 this way and then 5 this way. That tells me where the point is, right? Polar coordinates says this. How far am I away from the origin? Call it r. And what's the angle in standard position? Standard position means, like in trig, this is 0, and then positive is this way, and negative is this way, r comma theta. So if I pick any point in the xy plane, like over here, do you agree? I can find how far away from the origin, and I can determine the angle in standard position. So we're calling that r theta. So instead of x comma y, we have r comma theta in polar coordinates. Okay, so the main thing in polar coordinates is we're using r theta. So this is polar, and this is our usual rectangular, sometimes called Cartesian, x and y. So here's a point. How do I label it? Well, how far do I go this way? How far do I go this way? Polar coordinates, how far am I away from the origin? And what's the angle in standard position? So that labels any given point. Okay. A little bit of terminology. In polar coordinates, the origin is now called the pole, technically. It's really the same thing as the origin. Because I'm not going to take off points just because you don't call it the pole. It is the origin, but technically, very technically, in polar coordinates, the origin is called the pole, P-O-L-E. All right, well, I do see some relations. There's an obvious Pythagorean relation, x squared plus y squared equals r squared. Okay. On page 660, box 2, put both of these on your next cheat sheet. R squared equals x squared plus y squared, or x squared plus y squared equals r squared. Pythagorean relation, right? X, y, hypotenuse. X squared plus y squared equals r squared. Put this on your cheat sheet. Although, well, you don't use it that much, but there's some problems involved that. Tangent of theta equals y over x. Tangent of theta, well, tangent is opposite over adjacent, so y over x. So that makes sense. Okay, so put down tan theta equals y over x. Tangent theta equals y over x. Okay, then let's see what else I can come up with. How about cosine of theta? Cosine from trig is adjacent over hypotenuse. So cosine theta is x over r. If you multiply both sides by r, you get this. X equals r cosine theta. And likewise, if I start from the beginning, I say, what is the sine of theta? Well, sine is opposite over hypotenuse. Sine of theta is y over r. And if you multiply both sides by r, you get this. Okay, so here's the next thing you want to put on your cheat sheet. Okay, so in polar coordinates, x is equal to r cosine theta, y is equal to r sine theta. All right, so this gives us a way of transforming one system to the other. So if you have to go from rectangular to polar coordinates or vice versa, you have these formulas, right? X equals r cosine theta, y equals r sine theta. And r squared equals x squared plus y squared. Tangent theta equals y over x. Okay. All right. Now, there is one thing that's a little bit unusual about polar coordinates, and that kind of fouls us up a little bit. If I pick a point in the xy plane, there's only one way I can label it. So if I just have any, let's scratch over here. Make up any point like that. In the xy coordinate system, xy plane, how many ways can I label it? Well, there's only one way. You just count, how far do I go this way? How far do I go this way, right? 1, 2, 3, 4, 5, 6. So the only way I'm allowed to label this point is 2, 6, right? How far do I go x direction? 2. How far do I go in y direction? 6. Okay. It's unique. However, that's not true for polar coordinates, and that will sometimes foul us up. It'll mess things up. Okay. Here's theta. Let's pretend this is 30 degrees. Well, I could also go all the way around a circle and say 390 degrees. Okay. Or I can keep going again and again and again, or I can go negative also. So instead of, let's say, pi over 6, I could say negative 11 pi over 6, right? So you actually have infinitely many ways in polar coordinates to label a point if you're willing to just change the angle. Right? So I could go 37 degrees, or 37 plus 360, or 37 plus 360 plus another 360, or 37 minus 360 and minus another 360, and so on. Okay. And furthermore, we're even going to allow r to be negative. So negative r's, we're actually going to walk backwards. Okay, so we'll talk about that a little bit shortly. Okay. All right, let me at least show you the homework. We won't get that far. But 111, 15, 25. Okay, we have to go up to 63. So let me show you for the benefit of those of you that don't have the book and aren't getting it. Up to 63. Okay, just a side note, we're going to be graphing stuff like that. Okay. Maybe something like that. Different radius. So the polar graph paper I showed you had 14 concentric circles, right? So r equals a half, r equals 1, r equals 2. It's like a radius. The distance away from the origin, r equals 4. So notice anywhere along here, r is 4, and theta keeps changing, right? But anyway, I digress there. Oh, yeah, I might as well show this to you. One other formula that you're going to need on page 663. How do I take derivatives? Tangents to polar curves. So dy dx. Put this on your cheat sheet. Dy d theta divided by dx d theta. You don't really need this, but it's just showing you where it came from. It's like you take top and bottom and divide by d theta, so to speak, right? Divide top by d theta, divide bottom by d theta. And then where do these guys come from? It comes from differentiating these implicitly. Dy d theta, you can differentiate this. It's a product rule. Your meeting will end in 10 minutes. Okay, so I'm getting that thing again, so I have to finish soon. So if you differentiate implicitly and use a product group, this is dy d theta. And then over here, if you differentiate implicitly, you get this. The bottom line, for dy dx, do this. dr d theta sine theta plus r cosine theta, all over dr d theta cosine theta minus r sine theta. It looks kind of scary, but this dr d theta, once you get that, copy it over here. And r is just the original function. You copy that down here also. So that's what's going to happen there. But for the rest of today, let me just show you the homework. And we have to go up to 63. Okay, so it's on page 666. Let me get this for you. Whoops. Something happened. Got tapped out somehow. Let's see if I can go back in. I can't seem to do it. Okay. You've been having technical difficulties, in which case we'll just start tomorrow. Okay. Try one more time. All I was really going to do, fortunately, before that messed up, I got everything I wanted to do. The last major thing was just to show you the homework. All right, here we go. Okay, so 10.3, page 666. Okay. And there's that. And on this side, that. And this is where we're actually going to be sketching. Okay, so we'll sketch the polar graphs using our polar graph paper. All right, so get ready to have a lot of those. That's like 29 to 45-ish, something like that. Okay, and then let's see. I don't think we had to do those. And yeah, these problems at the bottom. Find the slope of the tangent line. Yeah, 55, 57, 59. And then horizontal vertical tangent 61, 63. Okay. Right, so there we go. Okay, and just to whet your appetite as to where we're headed, plot the point whose polar coordinates are given, then find two other pairs of polar coordinates of this point, one with r greater than 0, and one with r less than 0. Okay, so let me just show you one of them, then I'll stop, because I'm running out of time in about 6 minutes anyway. Okay. So number 1a, 1 comma pi over 4. Let me just show you what's going to be happening. One comma pi over 4. Now, the book doesn't use this notation, but I'll use it. A superscript with a P. Okay. P is for polar, R is for rectangular. Now, you might say, well, we never wrote that before. Yeah, because the only system that you knew of was rectangular. It was X and Y. But now that we're mixing up rectangular and polar, it's nice to sometimes superscript with either a P or an R. So if you look at this, you say, okay, that's polar as opposed to rectangular. Okay, now, even though it's given as r comma theta, you start generally with the theta. You can't walk out one unit, because how do you know which direction to go, right? Do I go one that way or that way or that way? So first you get the angle, okay? 45 degrees, pi over 4, and then I walk out one unit. So here we are. Now in the direction, it says give another ordered pair with r greater than 0. So in other words, I keep the 1. I got 9 pi over 4. Now, what is 9 pi over 4? That's going all the way around once. 2 pi plus another pi over 4. So 2 pi is 8 pi over 4 plus another pi over 4, 9 pi over 4. Look at another way that I wrote it with a negative r. Negative 1, 5 pi over 4. 5 pi over 4 is over here. So in other words, pi over 4 and 5 pi over 4 are 180 degrees apart, right? So you aim in this direction, and the negative 1 means you walk backwards. So we're allowed to have a negative value for r. It means you're going backwards. So 1 comma pi over 4, so it means I go to pi over 4, 45 degrees, and I'm aiming, and I go 1 unit. Or I can go all the way around 2 pi and another 45 degrees, pi over 4, so 9 pi over 4. So I could say I go all the way around to 9 pi over 4, and then I walk 1. But I can go 5 pi over 4 here, so I'm aiming this way, right? And then I go backwards. Excuse me. Right? So you're allowed to have a negative for R if you're willing to walk backwards, so to speak. So I aim in this direction, 5 pi over 4, and then I back up 1 unit. Okay, so that's where we're going to be heading starting tomorrow. All right, but otherwise, that's about it for today. I only have a little bit more than 3 minutes left. That's where we were going to do anyway. So let me stop the share. Any questions, please? Check the chat. All right, so we're done for today, folks. Okay, so have a good day, and we'll see you next time. Okay, all right, bye.
Thanks.